talk that's diving into dust versus AI. I know that dust might not on the surface seem like as big a topic of AI, but I talk about it every day, and seem to be fascinated by some of the chaos that dust causes. So I appreciate you all joining. So I'll give it just a few seconds here, and then we'll get started. Okay, I think I'll just dive into it so people can just join. So thank you for joining. Good afternoon, morning, evening, depending on where you're joining from. I appreciate you jumping on, especially after such a fascinating panel. I think I can speak for most of the people that are on the call, most of the people here. It's very common in a battery manufacturing facility that you're solving for things like energy density, for cycle life, fast charging, all of these, fascinating things that really impact your yield, really impact your product, and impact your customers. One variable is not often showing up in your data, in your electrochemical model, in your BMS data, or even on your quality checklist. Not until it's too late. So that factor, surprise, is dust. My name is Boris Pazovskiy. I'm the Global Key Account Manager here at Nilfisk. I am focusing specifically on the battery industry. Nilfisk has been around for 120 years. I've been around for 11 of those years within this company. And we cover all different types of facilities, all different types of industries, wherever dust is prevalent: pharma, food, metalworking, and of course, battery. So I've walked, dozens and dozens, if not hundreds and hundreds of factory floors globally. And one thing is for certain: contamination is one of the most underreported, underestimated risks that people tend to overlook until it's staring them right in the face. And it's not because people don't care. It's not because engineers are careless or quality folks really aren't in the know. It's mostly because a lot of the times the things that we're defending against here that are impacting your yield, impacting your safety, impacting your financial statements is invisible. So it's very difficult to defend against a defect that pops up later in life and is invisible. So it's very apparent that the industry is scaling very fast. So more lines, more volumes, more dust that's generated. And the stakes have never been higher, because if you're looking at some of the applications that we have today, I mean, of course, electric vehicles, everyone talks about that, but droids, defense, medical devices, battery energy storage systems like we just talked about today, data centers, all of these things are becoming more and more electrified leading into the future. So the stakes have never been higher per se. So today we're going to talk about where dust comes from, how it kills your cells, and what you can do about it. So in the next 40 or so minutes, we're going to talk about why dust is a blind spot and why it matters to fix it now. We're going to go over a full process map that basically pinpoints every single major dust hotspot, from coding to assembly to formation and everything in between. Then we'll follow the journey of how a single particle becomes a thermal runaway event. And of course, one thing I would be remiss if I didn't talk about are latent defects. These things are particularly scary because it's a defect that passes your quality check, passes your QC, and ends up failing in the field, sometimes weeks, sometimes months, sometimes over a year later. So your defect that passed QC ends up being found on the field many weeks, months, or years later. Then we'll talk about, okay, you have this dust issue, you have these issues in your product lines. What do you do about it? How do you address it? What are the technologies that can do it? What are the placement of those technologies? What are the strategies? How do you keep your clean rooms and dry rooms intact with these technologies? And then finally, we'll talk about the self-serving portion of it, how Nilfisk deals with these applications, with these situations, what we consider after being around dust for 120 years. We've figured out a couple of things that are important, and strategies to decontaminating very precious product flows, production flows, like in battery manufacturing, pharmaceutical, very sensitive areas like that. And then I'll leave some time for Q&A. So hold your questions. If you have some questions, put them into the chat. And if we don't get to them within the time frame, we'll certainly get back to you with those answers. So let's dive into it. So before we get into solutions, I want to frame the problem and the problem that we're actually solving, right? Because it doesn't get talked about enough openly. So of course we're scaling, like I said, rapidly, faster than ever before. From 1 terawatt today, we're looking at 9 terawatts by 2030. So even at this volume, fractional yield loss equals billions of dollars in wasted material. And contamination, dust, debris, is one of the most underreported variables that contribute to these fractional yield losses. And sometimes they're not so fractional. So I want to paint a picture with these 3 data points that are listed here. These data points kind of tell a story of where dust enters, what it does when it enters your cell or your production line, and what can be achieved when you actually address these points, these dust contamination points. So 90% scrap at ramp up. This is not a new statistic. It's something that's been circulated many, many times. And it's still particularly shocking to think that 90% of material can get scrapped. When you look at it on a microscopic level, even a macroscopic level, it doesn't come down to just bad chemistry. Oftentimes it's linked to particulate contamination. And ramp up happens to be one of the worst conditions that you can have in a gigafactory. It's the worst conditions. You have dust from construction, you have new tooling, you have new technologies that are being mastered, you have processes that are kind of locked in, but the variables in those processes are still kind of ambiguous because you're trying to maximize everything that you have and doing it efficiently while learning on the fly. It's been proven through case studies, it's been proven in research studies that inline extraction of dust and contamination from day one is directly correlated to faster ramp stabilization over time. So you can reduce that scrap rate much quicker with inline extraction that's built into your system from day one. You don't clean through a ramp up, you clean through a ramp up, not out of a ramp up. You clean because this is part of your process. It's not a housekeeping issue. Then you have the second number on the screen. So things like your conductive metals, your iron, cobalt, your copper, your aluminum, typically they're smaller than a hair. So you have 70 microns wide is your typical hair. So the things that we're protecting against, that we're concerned about, that we're looking at, are typically 50 microns and under. What happens is these small metallic particles, they bridge the separator. Once they bridge the separator, most of you probably already knows what happens. It's a micro short. Maybe it's not so micro at times, but once you have a micro short because of anode and cathode interaction, what you have is field failure weeks later. Sometimes it's not on the field. Sometimes it's not in a car. Sometimes it's in a storage facility. And I'm sure you have seen a lot of videos that are terrifying to watch, but show you some of the impacts of that. One thing that's interesting here is that in your ISO clean room, 5, 6, 7, 8, whatever it is, in your clean room, you're measuring parts per million, you're measuring the air quality, but surface contamination is a completely different control point here. So that's where inline processing, inline cleaning, and I'll tell you exactly what that is and what that means because I mentioned it a couple of times here, but that's where inline cleaning is most effective. That's where we play, that's where your HVAC doesn't play. HVAC plays more in the actual air. Inline cleaning plays on the actual surface. And then finally, you have a 40% self-discharge reduction with inline cleaning. And here I'll talk about inline cleaning. So I will say self-discharge rates typically are your canary in the coal mine. If you see that your self-discharge is particularly high, that means that there is some kind of issue with contamination inside of your process, typically. And it's been shown that with inline cleaning, meaning continuous cleaning, cleaning that's tied into your process, continuously pulling or moving contaminants off of your product, has been single-handedly linked to a 40% reduction in that self-discharge. If you think about it, you have a lot of dust in the air, you have a lot of items that are just kind of floating around. And of course, if they land on your product, on your active material, it causes continuity issues because your active material is not communicating with one another, and you're not getting the same density as you would if it was contaminant-free. So inline cleaning is continuous, just to recap, and it's not an end-of-the-shift problem. It's not Boris climbing into your slitting machine and wiping things down with a brush, or using compressed air, which is worse. It is something that's integrated into your process. What ends up happening is that a particle that you don't see with the naked eye, it becomes a defect that is also invisible. It's something that you can't find, but then the field finds it for you. And there's some cases that I'll share with you later in this presentation that speak to just that. So everything today is about closing this gap before the field finds your defect. So from our experience in working with various battery manufacturers across the globe, we've defined a scale between low and critical risk areas. So what does risk mean? Risk correlates to the level of dust particles that are emitted by your process. So that opens up the door for these particles to interact with your product in a way that really isn't desirable, leading to, if not immediate, latent product quality defects and safety issues. So risk equals dust emitted by a process, interacting with your products, and then causing these latent defect effects. So we'll start off with mixing. Mixing, it's most apparent that you have dust issues in mixing because typically you'll see it in the air. You'll see it when the mixer is operating. You'll see it when you're opening up your big sack. So this is visible dust. What you don't see, of course, is the invisible dust, the things that are below the 50 micron particles that can contaminate your slurry. So this can happen very easily. It can happen from mixer to mixer. It can happen from an operator, treating this mixer, coming over to another mixer, or even the fact that once your blend is mixed and you have your slurry, you're moving it from section to section and it's not covered, which also opens the door for contamination. Everybody in the industry knows bad slurry is where everything starts. Bad slurry equals bad product. And this right here sets off a domino effect for all the other touch points that we're going to be talking about. Next, you have your coating and drying. So this is kind of where you're taking care of your foundation. So you have your web and your active material on top of it. So what happens if you have contaminants on your web before you're putting on your active ingredient, before you're starting to put that electrode on? What happens is it often doesn't adhere. Ideally, you want as little space as possible between the active material particles because, again, you don't have continuity when your active materials aren't touching. So when you coat onto an undesired particulate, you introduce that space loss. So that is directly tied to lower energy density. So think about it, I like to think about it as you're painting a wall, right? If you paint a wall, typically what you want to do is clean the wall first because if you don't, you might have debris, you might have contaminants on the wall. And if you paint over it, it might seem fine. Maybe it's a little off, it might not be an issue. But what happens over time is that debris can cause peeling. It can cause peeling over time, basically, and chipping over time. That's what I was looking for. So what might seem okay at the time, many months later, maybe a year later, that can peel up and cause problems. It's the same thing with your electrode, because you might not see it because it's under your active ingredient, but it's just sitting there waiting. Next, you have your calendaring process. This particular process, it's medium because there's no direct dust that's being generated by this process besides for when you're compressing. Yes, that can cause dust to go into the air, but really the issue here is the latent safety defect. The latent safety defect here is generated by these little tiny metallic particles that are just kind of sitting beneath the surface, waiting. Some of them are 50 microns, some of them are 20 microns, some of them are the size of the separator, which is 20 microns. So when you compress onto your web and you're pushing in these little tiny contaminants, what happens is you start having these little micro fractures. You have these little tiny cracks that are imperceptible by the human eye and even some quality check inspections. They're so small, they're small enough to start causing micro shorts. Those micro shorts, they're even small enough to pass your hypot test. They're small enough to pass a lot of quality control measures. And what happens is, over time, they make it onto the field. And when they're out on the field and they're getting stress tested in a real world environment over many weeks, many months, now you start seeing the issue. Now you start seeing this defect that happens over time. Slitting is a critical area, and you might say, oh, this is obvious. When I go to my slitting machine, it's clear. It's very easy to see that there's metal swarf. It's very easy to see that there's debris and scrap and all of these things that are accumulating. But again, the things that you see, those aren't the issues. Those are the things that you can see, so you can take care of them. The invisible dust particles in this area are higher than most. So think about what's actually happening. You're taking a knife, you're cutting or a laser, and you're generating dust every single time you cut. Maybe one cut, not a lot of dust, especially if it's a sharp blade. 2 cuts, also. Thousands of cuts, it becomes a lot worse. So think about if you're using a knife in your kitchen. I don't know who likes to cook, but if you're using that knife, for 3 times a day for breakfast, lunch, and dinner, 10 minutes each, you might not see much of an issue. It might be a sharp knife and it might be good. But if you use that same knife thousands of times an hour for hours a day for weeks at a time, you'll start noticing that the cuts aren't going to be as sharp. You're going to start having less clear edges on the thing that you're cutting. And you're going to notice that the blade is suffering. So if you take that on and extrapolate it on a higher level, that's exactly what's happening. And you're not even seeing the amount of dust that's being generated on that microscopic level. And what you're seeing is burrs, sharp burrs. You're seeing the folded anode tabs. You're seeing little tears here and there, all being due to these microscopic issues. And what you're also not seeing are these micro perforations that seem like a clean cut, but are kind of in that middle part of when the knife was dull and the knife is sharp. You're not seeing these micro perforations on the separator, these little tiny tears, which also introduce this possibility of anode and cathode material touching. Now, finally, stacking and winding. This one is a high risk area, also because of the dust that's generated when things are compressed, but also the further compression of microscopic particles when you're stacking things together or winding them together, because again, you're pushing things very tightly together. So if it wasn't done in the calendaring section, now you're in the stacking and winding session, now you're having more compression, and that can cause issues down the line, kind of similarly to what we talked about here today. Now, finally, we'll talk about formation, but not too much, because really there's not a lot of dust that's generated in these areas. Really, you're just trying to clear the environment as opposed to inline continuous cleaning. So I'll just move on from there. Now I want to show you these little animations that follow dust particles from the process all the way to a thermal runaway event. So here you see dust is being generated by your process, whatever that process is. I left it as completely ambiguous. So you can imagine whatever process you like, your favorite one. That particle generates and then is migrated from step to step. So if you started mixing, that particle might be in the slurry, it might be in the environment, it might be in the bin, and then it moves over to your coating and drying line. In your coating and drying line, now you have these particles that are sitting on your web, and then it moves on and on and on to different steps of the process. When it gets to some of those compression stages, what you risk is separator compromise. Again, these are little microscopic metallic particles that are sharp in their granulometry, and you see that they're very small, but they're big enough to make these little micro tears in your separator. Tears in your separator, by now, if you haven't put it together, it's bad. Everyone knows it's bad. Now, it doesn't really start off as like such a big event when you have a compromised separator. It can start off by showing itself as self-discharge. Maybe it's just not holding a charge as much as it should. Maybe the energy density isn't what it should be. But what you're not seeing is that there can also be these little tiny micro internal shorts that are just so small that they're not even showing up. And then, of course, once you have this event happen, it moves on to the propagation of this one internal short. Over time, more and more, it starts spreading to other parts of your pack, other cells. And now you have your thermal runaway. Thing is that this can be imperceptible for months at a time. So when you see these battery energy storage system, not plants, but the actual storage of those storage systems, like warehouses, you see a lot of them getting propagated out of nowhere. But it's not out of nowhere. It's something that can be linked to this very insidious, somewhat invisible issue. Now, contamination defects, they don't just show up at the factory gate, right? They show up in a customer's car. They show up on a plain ban list, as you've probably experienced yourself, or in a $1 billion or more recall announcement. So what you're going to be looking at here is over $8 billion worth of combined recall costs, all traced back to manufacturing irregularities that, the biggest thing here, past quality check. So these past quality check, they ended up in the field, and then they started having problems. So $8 billion is just the start of what it costs to get cleanliness wrong. So now, just look at the first example, Samsung Note 7. It's what I go back to all the time because I remember it quite well. Samsung had irregularly shaped batteries and manufacturing defects that landed them in the position that everybody, I'm sure, can recall, where people were complaining about internal shorts. There was fires. There was thermal runaway that was happening, propagation that was happening in those cells. And it was such a systemic issue that even when they changed suppliers and another battery manufacturer came in, the replacement batteries also caught fire. So this shows that it was something that was deeply embedded into their process that wasn't found even after a second supplier came in. The flagship line was killed. Airlines started banning not only their phones, but also all lithium batteries at points, just kind of like a pendulum swing effect to protect people. But the key takeaway here again, quality check was passed. Manufacturing didn't see the problem. The field did. Next, you have LG and GM. So this recall was linked to a torn anode tab and a folded separator. Both were invisible in quality control, mind you. So one of these things by themselves might not have been such an issue. Of course, it would be an issue if you gave it some time. But together, they passed QC, leading to $2 billion of recalls. 140,000 vehicles were recalled. LG ended up reimbursing GM the $2 billion. It was more like 1.9 billion, but $2 billion, sorry. And the whole bolt line that this was associated with ended up being discontinued. So this was one of those flagship cases where a supplier of the battery was held accountable and had to be financially responsible for this failure. So this was a manufacturing defect that could have been prevented. And again, it was due to a systemic supplier liability that passed quality check. Finally, you had one plant for LG in Nanjing. And again, you had a folded anode tab, passed inspection, ended up causing internal shorts. 15 fires happened over 4 different countries, and 82,000 vehicles were then recalled. So there was an attempt to fix it with a software update, but it didn't work. Full pack replacement was the only way to go. So one plant having one big quality control issue ended up with a global impact. So this is a common thread. It's not design. It's not chemistry. These are process cleanliness failures. They passed QC. All of them passed QC. Every single one of these recalls traced back to a manufacturing systemic defect issue. Again, that passed quality control. So I don't think any of these companies set out to manufacture a defective product. The defect was more introduced during manufacturing, right? It was not caught until it was actually in the field. So the question for everybody that operates within a Gigafactory is really, what is your contamination control strategy? And is it strong enough to keep you off the list? So this is just kind of a recap of what we were saying. So some of the consequences. Of course, you pass product QC. Over time, your product is stressed by the field. And then you have a field failure, which ultimately is tied to a brand failure. And then you have to spend lots of money, lots of time, lots of nerves to combat this PR nightmare. So now, for those of you that love data, I'm going to dive into some data here. For those of you that don't, just give me a couple of minutes and then we'll move past some of these crazy numbers here. But I think that it's really important to see what data tells us about contamination control impact. So 50% yield floor. Without contamination control, half of cells are scrapped. Half. So if you have half contamination, of course, you can't put that product out into the field because of some of the things that we just mentioned. This makes contamination prevention a core operational priority as opposed to just an optional upgrade or housekeeping. A lot of people think dust is housekeeping, but I'll share with you why it's not. 85% of pack material costs are clean materials. So that means that the vast majority of input materials into your process for battery pack production, for battery cells production, must remain uncontaminated to be usable. So that means that the contamination events don't just cause defects, they destroy one of the most expensive parts, if not the most expensive parts of the cost base. I'll skip this one because we already talked about self-discharge, but this is a direct measurable yield improvement. Just by having inline cleaning, you can already start pulling one of these multi-million-dollar levers. And now we'll talk about some more advanced ramp-up scrap rates. So going down from 90%, some better companies, better Gigafactories start seeing an improvement, going down to 15 to 30% scrap at ramp-up. This can also be improved even further. Some companies, many companies, after 5 or so years, start seeing 10%. But the thing is that 10% might seem like a lower number, but you're scaling up from maybe you were at 10 gigawatt factory, now you're 30 gigawatt factory, 50 gigawatt factory, but now you're doing 10% of that 50 gigawatts, which is still a heck of a lot of material, a lot of scrap, a lot of dust, a lot of debris. So if you've had a problem on the original side of things, that problem persists, maybe not as much because you've started dialing things in, but it's still something that lives there. Contamination waste is still persistent. It's not just a ramp-up problem. To talk about some of the financial aspects of it, it's been found that even 1% of a scrap rate reduction per gigafactory can save a gigafactory 10 million euros per year. So every point is a 7-figure lever that you pull. Every percentage that you drop gives you lots and lots of money that can be used for R&D, new innovation, paying your people, anything. To further expand on that, you found 300 million euro in annual savings from a 10% scrap reduction at a 30 gigawatt scale. So what this means is that this contextualizes the ROI on process cleanliness. The savings potential dwarfs any kind of investment that you might put towards the cost of filtration or your cleaning equipment, because you're saving so much in your material and not having recalls or PR nightmares down the line. Now, 1 micron. 1 micron is all that it takes. It's the threshold for a short circuit to happen, whether it's a micro short or a propagation event. Submicron filtration is non-negotiable. It's something that is necessary when you're working with some of these materials that we often see in gigafactories. Now you see the economical and physical repercussions of this lack of dust control. Let's take a look at the various areas that are impacted most by appropriate decontamination. So there are 5 main factors. So just to kind of drive home the point that this is not just housekeeping. This is not just dust that you see in your house and you wipe your finger on it and you're like, okay, I need to dust, I need to vacuum. No, in an industrial setting, it's linked to product quality. We've already beat this horse to death. You've already heard me talk about lower energy density, lower energy density, higher yields, all the things that come with better product and product quality. Uptime, of course, if you have a lot of dust and you have to take time off because your production line is closing down, your product isn't working out the way it should be, you're seeing a lot of contaminants surfacing and your product is failing its testing, then of course you're going to have downtime, and that's to be avoided at all costs in many facilities that I've been to. And then you have the worker exposure side of things. So worker exposure is extremely important, especially where in the field that I came up in, pharmaceutical, but even also in battery manufacturing. If you're working with cathode material, if you're working with NMC, if you're working with DMC, if you're working with any of these things that are very bad for your health to breathe in, of course, you want to make sure that your workers are coming into work in the same condition, if not better, maybe morally in some kind of way, than when they're leaving. When you're working with combustible dust like graphite powder, carbon black, things of that nature, you want to have the appropriate equipment in place to make sure that the equipment itself is not going to give you a risk of combustion, because these powders are already in and of themselves susceptible to being flammable, combusting, causing not just a thermal runaway event, but an actual explosion. And finally, companies spend so much money on clean rooms, on dry rooms. To maintain those things, there's millions of dollars to get it built, and then also, of course, to take care of it. So you want to make sure that the equipment that you have in the room is keeping that environment clean, is not a contaminant itself, but it's also not emitting heat in a way that's compromising your dry room, right, and messing with your dew point. So now I'll talk about kind of what we do and some of the things that we consider when we're walking into a battery manufacturing facility. We're looking at the production lines, and we're talking about some of the approaches that you can use. And vacuums aren't the only one of them. There's air blades, there's contactless cleaning. There's a lot of different technologies, but it's been found through research that is actually cited at the end of this presentation. You guys can take a look. But vacuum is the preferred method, and it's the most effective method for cleaning processes in line, and has been linked to the most efficient reduction in scrap rate and latent defects over time. But the vacuum technology that you choose is very critical. It's as critical as the process itself. So getting it wrong can lead to some of those problems that we spoke about before. Compromises in product quality, creating an explosion hazard, or generating compliance exposure, which can be very costly. So now I'm going to map out 6 purpose-built vacuum solutions to specify towards the battery manufacturing processes that they serve, right? So first, you have your general all-encompassing workhorse vacuums. These are your, again, sub-micron filtered vacuums. So they use either HEPA filters or ULPA filters at times to capture fine active materials. Oftentimes they have sealed bag systems, so you have some level of containment between you and what you're picking up. Then you have your clean room. Again, these are meant and designed to not be contaminants. They're meant to clean the room and not add to the particle emission in it. So it's made of very specific materials. Then you have your high volume vacuums. These high volume vacuums are centralized extraction systems. So it's one big system that gets piped into various parts of a process or various different processes at the same time. Think about 30 or 40 different pickup points, hoses, things like that. And then you have your explosion safe. We already talked about this, but it's your explosion safe vacuums that are ATEX rated, NFPA compliant, to the different directives that are relevant to the countries that they're in. This one is very, very important for us. It's a slitting machine integrated vacuums, and really they're more of your high volume vacuums, but are very strategically placed as far as where the pickup points are, because it's a very sensitive process and it generates a lot of dust and can be linked to most of the defects that you have within when it comes to folded anode tabs or torn anode tabs, or latent defects in thermal runaway, things of that nature. And finally, you have automation. Automation speaks for yourself. You have your robot, you have your arm, you're moving your vacuum from place to place. And then you have your Nilfisk. I'm sorry.
No, chiudi per favore.
I'm sorry.
Non me lo ricorderò mai.
I'm sorry. Can we mute ourselves? Sorry, I'm just picking up some noise. So now, how do we address this? I'm sorry, can we mute ourselves? I'm hearing some stuff, but anyway, so how do we address this from the beginning? First, we have to go into a facility to discover and process
Chiudiamo le
the
finestre,
applications.
evidentemente.
Cesare, can you please mute yourself? Sorry. Sorry. So first we have to map out the process. So Nilfisk walks in and actually takes a look at every single process step to identify any kind of airborne particulates, the types of particulate, the quantities of particulate, whether they're combustible, things of that nature. Once we have a good assessment of what that looks like, we actually engineer and for that specific application. So we engineer, say you have a slitting line and you need 40 different pickup points, which is an example that is very specific that I'll share with you. We engineer it so it's fully balanced so you can get the right air velocity at every single point that you're picking up from. And to prove the concept, we do trials, we validate our recommendations, and then we take that solution and we scale it up to the different parts of your facility. And if you're scaling up, we scale up with you with larger and larger machines that can address those applications. So now I want to go really quickly into a case study. I'll just do one, I have a couple, but this is a customer who had, again, this is a slitting line, but they had 40 different pickup points that they needed to address, all of different sizes, some for turbo brushes, some for blade units, some for under the roll, and they needed it to be a certain speed at every single pickup point. For anybody that knows anything about vacuums, or even if you don't, typically the point closest to the vacuum is going to have the most suction. The point at the last point, so at the C section here, will have the least vacuum. So how do you balance it for a customer to have the same pickup velocity, the same airspeed at each pickup point? Well, you have to size the vacuum the right way. You have to look at all the different areas that are generating dust, and you have to size the tubing and place it in the right way, in the right places for 40 different pickup points to absorb some of that or all of that dust. So it's not a contamination issue anymore. So what we did is we ended up doing just that. We ended up having one of our big boy, this is a centralized vacuum, usually meant to power a large facility. But in this case, you needed it to power the slitting machine and divert the airflow from the vacuum inlet all the way through to the turbo brushes and the blade units, so you can have that strong suction. Once you have the suction determined, then you can start kind of introducing the valves and automation measures that allow you to ensure that you're getting the same suction, the same velocity at the inlet as you are at the end of the line. So this takes quite a bit of engineering. It took a lot of visits, a lot of back and forth with the customer to understand exactly how this would work out. I was really impressed with our engineering team actually for figuring this out because it's not easy. So this actually addressed a part of the slitting machine, and then we had another system that was dedicated to the other part. So again, same kind of approach. We needed to break down the airflow so that we can bifurcate, trifurcate, Y-split, three-way split into the machine to collect from every single point in the same air velocity. So again, this was a very engineering intensive approach that we took. And it helped save the company a lot of money because they were really struggling with their energy density and their yields. And after we introduced the system, they saw an immediate uptick. And even months afterwards, they were still thanking us for introducing this type of system into their production line because they didn't even know where to start. And they're very smart people, very big company. I won't go into this because I know we're kind of running short on time, but this was a dry coating application, but there's applications that are literally limitless from the beginning of the production line all the way to the end to formation. Wherever there's dust, that's where we're playing. So I'll go into all the key takeaways real quick. I'll fast forward. But dust is a safety and yield issue, not a housekeeping issue. Hopefully that's something that's stuck with you. It sits kind of at the intersection of self-performance and process uptime, worker safety, and fire risk. Then every process step generates contamination, but not equally. As you saw, slitting was a lot more prevalent than other steps. Latent defects are the hidden cost. Problem is that latent defects by nature are only showing up later on in the life cycle of the battery. So that's what leads to these recalls, leads to these issues. And unfortunately, you can't even see them inside of your process line. Then you have what we just talked about, the cleaning technologies that help make the lives easier, help increase that energy density, help mitigate some of the risks with thermal runaway. Typically, a vacuum is the preferred solution. And then always you want to take a look at the process. You don't want to just purchase something online without having somebody take a look at your process and actually walking through everything, because this is a very intensive engineered solution, and it's custom built typically for the process, for the environment, consideration of the factors that we just talked about: ATEX rating, sizes of particles, prevalence of the particles, and things of that nature. So with that, I know we're kind of late, and some of you might have questions. I don't know if there's any in the chat, but I'll leave them open while we're here, if you guys wanted to stick around. Any questions that I can help answer?